Alright, in this video I will explain why we cannot assume the conclusion of a theorem or proposition in a proof. This seems quite trivial, but I keep seeing students making this same mistake over and over. First of all, let's see an example. Okay, so here's a proposition we want to prove. Let's say m and n are some integers. Actually, it can be any integers. If m squared is equal to 2n squared, then m is even. This proposition appears when we want to prove that square root of 2 is irrational. But anyway, we are just interested in this part. Okay, so let's give a proof that makes absolutely no sense. Okay, so this is a wrong proof. Nonsense. Okay, so suppose m is even. Okay, here we are actually assuming the conclusion. Suppose m is even. Then that means m is equal to 2k for some k integer. Okay, then let's substitute this into this equation. Then we have so 2k squared is 4k squared equal to 2n squared. So compare this. So this is again wrong argument. So compare this with this. We have m squared is equal to 4k squared. Actually, we came back to our assumption here. Therefore, m is equal to 2k. Actually, this is wrong, because if this is true, then we should have m equal to plus minus 2k. But anyway, it doesn't matter. I mean, it is just simply everything is wrong. So we are just adding another wrong point. This indicates, therefore, m is even. Right? And proof is done. This makes no sense. It's a nonsense. But I keep finding this kind of proof in my class. So what is exactly wrong with this proof? Okay, so let's go back to our original proposition that is to be proved, this one. Okay, so this says if this is true, then this is true. Okay, so let's put this as a formal into a formal logical statement. So let's say P is a proposition that m squared is equal to 2n squared, and Q is another proposition that m is even. So what we want to prove is actually if P, then Q. So we want to prove this one. However, look at this wrong proof. In the beginning, we assume that m is even, which is a conclusion. And then we concluded that m is even, right? So what we are actually doing in this wrong proof is that if Q, then Q. So if you write down the truth table of this logical proposition, we have this Q, and Q implies Q. So Q can be true or false. Okay. When Q is true, then this is true and this is true. Therefore, this implication is true. This is according to the definition of this implication, right? And if Q is false, then the premise here is false. So whatever, and also the conclusion is false, of course. But if the premise is false, then this whole proposition is true. Okay, so this means this proposition, if Q then Q, or Q implies Q, is always true regardless of the truth value of Q itself. Okay, so such a logical statement is called tautology. And this has no new information whatsoever, and it's quite useless. Why is it useless? Because, we wanted to prove that M is even. But this statement, this tautology, is true even if Q is false, right? So that means even if M is not even, or that is, even if M is odd, still this statement is true. Okay, so this proof is, in a sense, true irrespective of the validity of this conclusion. Okay, so this doesn't, in other words, this doesn't prove anything. Okay, so that's why this is wrong. Okay, then what is the correct proof? Let's show that. This one is correct. Okay, first, suppose M is odd. Okay, not even, This is, suppose this is odd. We prove by contradiction, actually. Then we have M is equal to 2k plus 1 for some integer k. Okay, then from the given equation, we have 2k plus 1 squared is equal to 2n squared. And if we expand the left-hand side, we have 4, k squared plus k plus 1 equal to 2n squared. Now, the right-hand side is even, obviously. It's a multiple of 2. However, the left-hand side, so this part is even, and even number plus 1 is odd. So the left-hand side is odd. But this is a contradiction. So this says odd number is equal to an even number. This cannot happen. Therefore, our assumption was wrong. That means this assumption was wrong. Therefore, M is even. So this is proof by contradiction. So why is this proof correct? Let's go back to this statement. So if we define propositions Q and P as this, what we want to prove is this. Okay, if P then Q. However, this proposition is equivalent to its contrapositive. So not Q, then not P. Okay, so not Q here. Not Q in this case means not M is even. So that means M is not even. So that means, so this means M is odd. That is actually the assumption we have made in the beginning of this proof. And from that we derived that not P. So not P in this case means, so P is this one. So not P in this case means M squared is not equal to 2n squared. So that is actually what we have derived here. You know, assuming m is odd, then we derive that m squared becomes an odd number, which cannot be equal to an even number. So therefore, m squared, if m is odd, cannot be equal to 2n, right? So this shows that m squared is not equal to 2n squared. It just cannot happen. Therefore, we proved that this implication holds, which means we have proved the original proposition. So that's how proof by contradiction works.